I'm going to take a little bit different tack than maybe a computational science tack. I'm going to be talking really about how the future of instruments and computing get put together. And so this has been called edge computing in many venues. And there's a particular project I'll be highlighting, which is the SAGE project. And it's an NSF project out of Northwestern University. And there's a large group of collaborators. I'll highlight them as we go, but let's dive in and look at instruments. So I was told that it's okay for this group to be interactive. So first, if you know where this is, blurt it out. Antarctica, right. So this is a big experiment in Antarctica. And the data has to be processed at the experiment because data out of Antarctica is pretty slow, right? You get a small slice of the satellite link, right? So you have to process data here. And so they actually have a cluster in this facility that's running the analysis in situ, right as the data is generated. Now, the strange thing about this particular data center is this is one of the only data centers you have to heat. You don't cool the data center. Because if you let it cool as it would normally cool, everything would break, right? So you heat the data center. Is anyone familiar with this kind of experiment? Have you seen these towers before? Maybe you're part of QAnon, and you know what this is. It's looking at, no. So this is the NEON project. The NEON project is a project to understand the ecosystem of the United States. It's run by the National Science Foundation. And primarily, what's happening in the ecosystem and in the atmosphere outside of where man is changing things. So in the natural as we can get. So the towers, these are instrument towers, are not placed near cities or against the highway because you're going to measure you're going to measure human activity. We want to understand 30-year range, what's happening with ecosystems. And so scientists go out, they have these towers, but they also do real field work, like they go out with boots and galoshes and pick up frogs and weigh them, and they gather plants, and there's this enormous bank of information about how the ecosystem is evolving. Now, the interesting thing here as well is they have a lot of instrumentation here, and they have an instrument hut, and this is a distributed network. And they have to sort out, how do we put computing into the network, right? So we have to put this not just at the South Pole, but how do we add and inject computing in the instrument when the instrument is distributed in random places all over the United States? One more example, which place is this?
LSST, isn't it?
Pardon?
Is it LSST?
Yes, right. So this is the Vera Rubin telescope, and in this particular case, they do have fantastic fiber, right? So they have a fiber link. They do still have computing locally, but there's a fiber link, and it goes all the way and up to the United States from Chile. And there's NCSA is processing that data, I believe, in sort of mostly real time. In other words, they get to process that data locally, but there's also additional processing done and data at NCSA. But again, in all three of these examples, there's a large instrument and there's computing that has to be associated with that instrument. And this is a little bit different than the way we've traditionally, by traditionally meaning 30, 40 years ago, done instrument analysis. Traditionally, we would gather data, write it into a lab notebook. Sometime later, someone might process that data and then work on theories or computation that gives us insight. But what we have now is a new kind of computing paradigm. We're used to, this group here is used to computing on the supercomputer, right? There's large-scale computation happening over there on the analysis side. And that's a simulation or a model or maybe AI training. But in all of these cases, the systems now have to be linked. We have, whether it's a very large telescope or it's something small like an IoT device, there's processing that's happening at the edge, and then there's processing that's happening on the supercomputer. And that's a new programming model. And there's a new cyber infrastructure, a new computing infrastructure that has to go along with supporting that. Sometimes this is now, lately, being referred to as the digital continuum or the computing continuum. And you might be familiar with this in the commercial space. This is happening in how cell towers are talking to your cell phone. So right now, in the old way, if you were going to connect with your cell phone and play a video game or play a multiplayer game, you're sending all of your packets from your phone game to California, part of the game, and back. Now, what companies are doing, just like what's happening with Netflix or streaming providers, they're moving those interactive services into the cell tower. So that's a different kind of edge computing. So your phone, if you want to play a really low latency multi-user game, your phone is interacting directly with a virtual machine that might be in the cell tower so that you could get interactivity among other people immediately. So this concept of writing programs that span from the edge to the cloud is pervasive. It's pervasive in the commercial space, but it's especially needed in the scientific space, given how much data we have and the kinds of instruments that we're building. So this is often, as I said, referred to as edge computing. And what's made this really possible and really transformative recently is that we have AI to help with that analysis at the edge. So if we were simply trying to do the kind of computing simulations that we're used to on the supercomputing at the edge, this would be very difficult indeed, right? But what's happened is we can train up networks using all the data possible, do that training of a model on the supercomputer, move only the model out to the edge, and then do inference at the edge. And inference, as you know, is much, much cheaper. Right? I can do that fairly quickly, often in microseconds or milliseconds, depending on or seconds even, but depending on the model. So I can do the heavy lifting of training on the supercomputer and then inference at the edge. So what are all the reasons why you might do this separation? Well, I mentioned the easy one, right? So you have more data than bandwidth. That's easy, right? You have to process some of it. And almost all of these big experiments, these big instruments, have way more data they generate than you can possibly save. And I'll just give you one example from that neon tower that I pointed out. They have instruments that gather data at about 20 or 30 hertz. Now, that's not a big number. 20 or 30 hertz, a couple, that's not for us, that's not a big number. What they normally do right now, even though they're gathering data at 20 or 30 hertz, they average it over 30 minutes and send one value back. Now think if you're the scientist who wants to explore the data and you get one value that's been averaged over 30 minutes. Right? I mean, it's just painful, right? The kinds of things, with all the interesting perturbations that could happen and that do happen in the data. And so bandwidth is a key one, but another one is latency. There are things that we want to do in experimental control at an instrument edge, and we can't wait for it to go back to the supercomputer. So, I mean, all of you recognize this is the case if you were to imagine a self-driving car, or you have a Tesla, or maybe someone you know has a Tesla. If you were imagining that the car has a camera and it sees a stop sign, it's not sending an image of the stop sign to California, right, and then determining it's a stop sign and sending it back to your car. That would be very dangerous indeed. It has to have the model built into the car, right? The inference engine is built into the car. So all of commercial devices now that are intelligent are doing this, and latency is a key part of that, not just bandwidth, latency. Another one is privacy and security. We like the idea that we can inference and then throw the data away, right? You could see that there's a human at a intersection, right? If you're in an urban environment, and you don't have to actually know which human it is, you just need to know there's a human at the intersection. So privacy is a nice feature as well as being able to do AI inference at the edge. There's also a resilience feature. So if you send everything to be processed to the data center, you know, we like to call that a single point of success. Well, that means that if it doesn't work, well, you don't have a single point of success, right? But you really would like to be able to cut the city, if you had sensors all over the city, or that big outdoor network, to cut that in half. If something happened on the network, the other half would still be processing data. And finally, there is a power savings feature with edge computing that happens when you have things that are very, very low power. They can watch for interesting observations, interesting events, and when it finds something, then they fire up the radio, then they transmit it. So they don't have to be transmitting all the full data stream. Okay, so we'll talk a little bit about one of these projects that is building this network that goes across this. The SAGE project is an NSF project. NSF has several ways that they fund things. This particular method is a research infrastructure. So it's being built to try new research. And in fact, this picture here is kayaking on the river right here that we take the students and do in Batavia once every year in the summertime when we have all the students locally. This project is spread out over California, Oregon. We have volunteers in Oregon. We have people in Utah, in Colorado, in Northwestern University, University of Chicago. So there are really great hard computer science problems here. And we're going to come back to this, but you know, right now we're talking about the high-level pieces, but there really are deep problems I hope we have some time to talk about when we finish up in the question time. So maybe I'll come back to this when we get going. So this project that is SAGE is building on something that happened in the city of Chicago years ago now, which was the very first sort of intelligent city project. It was led by Charlie Catlett, and it ended in 2018. And it was to put the first kinds of these sensors out in the city to try edge computing in this first way. Now, at that time, we didn't have a super fantastic, powerful edge computing node. So we were using essentially an Android single board computer phone. Now, it wasn't a phone, it was a board that came out of South Korea called an Odroid, but it was a pretty weak, it's like a little bit better than a Raspberry Pi, right? And it just really didn't have the power to do real edge computing. There we go. And so when we started the SAGE project, though, we came to this question, okay, well, the Array of Things project got us launched in this space, but that we were studying urban, but as we move out to these towers, like the neon towers, what we're really trying to do, and we started working with the scientists, we really want to write a software-defined sensor. Scientists at that time for these towers are used to buying a CO2 sensor, a moisture sensor, a CO2 flux calculation. The idea that you could write a piece of software that would tell you, okay, what's the cloud cover? That's a new kind of sensor, a software-defined sensor. And these examples here are real examples from students who were working on the project at the time. So whether it's using the camera to identify plant species, pedestrian flow, bird song, we'll get to traffic flow, wildlife, detecting smoke, water. All of these are essentially software-defined sensors that represent algorithms that have been moved out to the edge. So to wrap up that part of the intro on the project is to build this cyber infrastructure where I now have a programming model that allows me to write supercomputer programs that can connect to edge programs, and those edge programs are dynamic, so I could write myself a birdsong detector or write myself a bat detector, right, by analyzing ultrasonic sound, right? So that's the project, and now let's look at some of the partners and then dive into examples. So we, of course, are continuing our collaboration with the City of Chicago. So the City of Chicago, the Array of Things project, that group is continuing. Another partner that we have is the San Diego Supercomputer Center and a network they have in the mountains there that specifically, it's a wireless network that hooks up like the observatories and even Forest Service land, but they've now retasked that as well to look specifically for wildfire. And so they have a whole set of cameras that are called alert wildfire cameras. And the Oregon folks, who are on the other side of that picture, also have a series of these cameras, but the Oregon folks are not just interested in wildfire, they're also interested in earthquakes and mudslides, you know, all the dangers, right, from living out west. And then in the middle there, or to the edge, is NEON, and that represents those big towers distributed all over the United States. So those are our partners in this project. And to build that edge computing capability, I mentioned that we have this software infrastructure we have to build, so from edge to supercomputer, but we also have to deploy it. I mean, it's a real infrastructure project, meaning you have to make it go work, right? So you have to build things. And so we have two ways that we've been doing that. Over here on your right is essentially it's a pure software. We deploy a commodity blade in their instrument hut and can start processing the data with a GPU right there at the edge. So in this case, we happen to get a deployment when there's a rainbow. I don't know how often that happens, but they've opened up the telecom cabinet and they're putting that Dell server blade into the cabinet. And now our server, which is again just a pure software just running on a commodity x86, is going to process all the data live that they get from the instruments. So that we refer to that as a Sage, you know, blade. It's just a computing blade that goes in. It's a software play. But on the left is a GPU that's been stuck in a plastic chassis so we can strap it on a pole. Okay, so if you don't have an instrument hut that is a nice telecom hut, we need to be able to put it outdoors and put it somewhere. And so in this case, we take a Jetson NVIDIA, Jetson NX, and so this is a mini, you know, GPU. It's the same technology that's in an A100 or something else, right? Except it's scaled down to 30, 50 watts. And we can put that inside this node, and then we can strap some sensors on as well. But again, this gives us the capability to add all the sensors and feed the sensor data in. So it has 4 power over Ethernet ports, so we can plug all these different power over Ethernet sensors in. So we have 2 kinds of platforms. And our architecture is fairly straightforward in the sense that we want as much as possible to have a standard Linux environment on the node. Because again, the difficulty here is we're writing a capability where a programmer, like yourselves, could write a piece of code that is on a supercomputer and then write a piece of inference engine that lives on the edge. So what do you need? You need Linux, you need PyTorch, you need OpenCV. If you're doing something that's not deep learning, but maybe just standard computer vision, you need TensorFlow, something like that. And we're using Kubernetes to do all of that launching. So then the environment of the edge looks a lot like a cell phone in the sense that there's a way to package up, like an app, what you want to run, and then the scheduler sends that out to the edge nodes, and it runs at the edge nodes. So here is a picture here, and let me just double check this 1 second. Let's see where I am. Yep. So here's a picture of where we have the nodes deployed across the United States. We even have one, I know it's over, you can see at the top there, V006. So that's in the northernmost part of the United States in Ukiavik. There's a DOE site there, and so we have a server up there as well. We don't have an outdoor node because I think it would freeze, but we have a nice telecom closet for the node. And so we can get online. You could get online and look at the nodes and look at the data that's streaming in from these nodes. But remember, the goal of this project is to process that data out at the edge. Now, I mentioned that it's kind of like an app, like on your phone. So what do you have to do for an app? You need an app store. Well, it's not required to have an app store, but we have to package these things up to send them as bundles out to the edge. So if you're a developer and you want to develop code, we can't really give people SSH login to the edges because these are on mountaintops in places and it's complicated, all the networking tools. So what we want to do is you develop your code in a container, right? It gets containerized, it's in Docker, right? And our Kubernetes can launch it, and it's packaged up so all the messaging layers go through like your phone. It's making API calls to send things home. So that Docker container can then be from our store, right, from this portal. You can then take the Docker container and ship it out to the edge, and the scheduler then says, okay, we're going to run this. So here are some examples that we have coded up now running at the edge. Everything from using a standard YOLO object counter to the wildfire smoke detector or cloud cover. We'll talk about these, but these are examples. And actually, if anybody in this class is interested in writing a piece of code for the edge, we have nodes that are out in the wild that we do give people permission to log into. There's one in Utah on top of the Field Museum. There's one at Argonne. There's one in Oregon on top of the computing building. And so there are ways to actually start developing code for those edge nodes if you wanted to try something. So as I mentioned, we have deployments in Chicago, and this is an example this is on the corner of, let's see, I don't remember which corner this is. Oh, I think it's LaSalle and somewhere else. So this is Sean, who we have to get a hard hat, okay? That's safety first. We probably, now he realizes maybe I shouldn't stand underneath the bucket truck. But they're putting up one of the nodes and strapping it to a pole. It uses cell phone data in order to communicate. And we're streaming that data, and you can see that data on the portal right now. And what it does, again, it's running AI. This is now where the privacy piece comes in. It's going to run AI at the edge and give us pedestrian and car counts without sending all the data back, right? So it can do that inference at the edge and then throw the image away. This is a great project, another example that happened at NIU. And this is a pedestrian crosswalk where a node is looking at the crosswalk and doing real-time analysis of how many pedestrians and where they're moving. And then over time, building a map. Red is moving in one direction, blue is moving in the other direction. How do students really use the crosswalk, or maybe how do they don't use how often do they not use the crosswalk? And the project then also began to explore the water here. So you can see that the water in that drainage ditch or river, creek, you can see a shadow against the cement there. So if you apply the right kinds of algorithms, can you determine how the water's changing over time? Can you do that in real time? We'll come back to that in a moment. Another example is avian diversity, or knowing what bird species. How many of you here have loaded the Merlin app on your phone? The bird app. We don't have any bird? Okay, we have one. No eco-friendly, green, oh, I love birds, people. Come on. So you definitely should try this out. So if you haven't tried it, it's magical. So there's an app, no pun here, Merlin. There's an app here called Merlin. It is the University of Cornell are like the world's leaders in ornithology, right, in bird science. And they've developed a deep learning net, a neural net that allows you to record a piece of audio, and it tells you what species it thinks you're listening to. And so you load that up on your cell phone, you go outside, seriously, you go outside in the morning right here, it listens, you get to see the spectrogram, you know, immediately within 2 or 3 seconds it says, oh, that's a robin, that's a cardinal, and also it gives you examples that you can listen to yourself of a real, you know, an ornithologist says this is absolutely the bird, so you can sort of make your own comparison. It's amazing. So that model has been trained by the university, and we can take that model, Dockerize it, put it into the container, and ship it out. And in this case, we shipped it out to a node that's at a prairie near Chicago, and we can then get realize the AI is not perfect yet, but we can get a rough view of what's happening in the prairie. And so scientists are very interested. Again, you can't send all the data back. You can't possibly, especially if you have thousands of microphones. But being able to determine if species are arriving early, what species are there, what species avoid certain other species. You get a time window, right? You hear this species, do you then hear another one in the same window? Wonderful abilities, again, by linking what you've trained up on the supercomputer to making an inference engine out at the edge. And so we get lots of great examples here. This is the paintbrush prairie, as I mentioned, which is run by the Nature Conservancy. Another example is just taking a camera and looking up at the clouds. So atmospheric scientists care about this. I was surprised, like, well, it's a cloud, right? And I thought that maybe that the highlight of atmospheric science might be what kind of cloud. But determining the level of cloud and the boundary layer and at what rate they're moving, even if they're not moving, you know, together, like one layer can be moving this way, another layer can move another way. You can do that with a camera with the right kind of AI training. And so here, a scientist at Argonne, Scott Collis, working with Bhupendra, a new postdoc, came up with a way to calculate cloud motion vectors, which give us a very interesting vector of the cloud, where it's moving across the whole sky, across the image. Now what's difficult, these images here are because it gets cold and it gets frosted or it gets rained on. And so the AI has to be able to determine whether or not you're actually seeing clouds or you're seeing artifacts. And of course, you're getting training data back all the time to improve the algorithm. And so what you see in the camera facing up might sometimes surprise you. You know, as Bhupendra is looking through the data and wondering why certain data looks the way it does, you can go back to the training data and find out, okay, I see where the model went wrong, right? And you know, if you wait any longer, it might go really wrong, right? I mentioned the snow depth and I mentioned water depth. This is another example of using AI trained on the supercomputer, pushed out to the edge. All over the United States are places where there are metrics stuck in water or in snow, and humans would go out and send grad students out, of course, to go out and tell me how deep the water is, tell me how deep the snow is. Now you would think, okay, well, can't they come up with a sensor? But the likelihood of the sensor getting fouled is actually, it's much easier to just have a stick and have a human go. Because a sensor, especially if it's in moving water, there are twigs and leaves, and it's very difficult to get level. It's a pretty expensive sensor to do that. There are ways to do it. But with computer vision, we can take these existing sticks and existing cameras and start processing it to get live data. So Songha, who works at Argonne and Northwestern, takes this real data. This is from the neon towers. So some of the towers are near water, and processes it and created this set of algorithms which takes the stick, finds the stick, finds the edges as needed, produces a labeled and masked way to compare, and then builds this model so that she can calculate what's the stick actually reading right after it gets calibrated. And so again, writing a computer algorithm that lives at the edge, she's written a software-defined water depth sensor. Another example, this is a ball field in a sort of economically disadvantaged area of Chicago where they have bad flooding. So the city has not invested heavily in the water system there. And so this is a local park. Unfortunately, when it rains, it floods. They'd like to be able to build hydrological models that look at water, that look at the soil moisture, and then calculate. Can we predict ahead of time, 3 or 4 hours ahead of time, hey, the field's going to flood. We have to clear people off, or we have to cancel what's happening, or maybe we know how to mitigate. In a more tragic problem is when it floods like this, it usually floods into people's basements. And when Chicago floods into people's basements, it's not water. So the Chicago system is something that's called a combined system. Of course, you know what one of the things that it's combined with is rainwater. The other is what comes into your basement, right? It's from the sewer system, unfortunately. So a lot of cities have separate, what's called sanitary sewer and drain water, that comes storm water. But in Chicago, because of the way it was built long ago, these things were combined. And if those of you who are trivia folks, you might know that occasionally, once or twice a year, it actually overflows into the Chicago River, right? So it's a real problem in being able to calculate and understand when flooding happens. And of course, we know about how tragic it is when you have no warning about this. What can you do from ability to run algorithms at the edge? Could you improve that? There are also people who are looking to use this kind of capability to understand wireless and the next generation 6G, 7G. How would we create new spectrum protocols? And again, you have to run processing out at the edge to do that. And now we'll talk a little bit about the wildfire. This is the kind of science that is both challenging and hard, but you really understand the impact that you might have if you have a breakthrough. So this is very exciting science. So the wildfire group that is leading in this space is out of San Diego. It's Ilke Altintas group. They have a project called WiFire. And they also are working with these alert wildfire cameras. And the other group out of Oregon, the Oregon Hazards Network, they're both partners in this project. And we've been working on how do we train the image recognition to understand smoke. This is a hard problem. So if you think about how you do visual training, you're familiar with sort of the cat-dog, right? Okay, I need to label a bunch of images cats. I need to label a bunch of images dogs. How do I do that? Well, I ask the internet, right? And you can find groups of images that are labeled clearly, right? You can find them on Flickr. You can find them on YouTube. There's lots of ways to get data. If you want to get wildfire data, first off, it's hard. It's sparse. But second, you need a human who's maybe an expert who can go in and understand that this happens to be smoke, while the cloud that also can sometimes look white or black is not smoke. And it's very tedious. So the project has been using humans to label images, thousands and thousands of images. But there's a kind of machine learning that is very attractive in this area. And that kind of machine learning is the ability to take something that is ground truth. So this is an infrared camera. And I know for certain, because I know the temperature of this section right here, I know for certain that that's smoke. So now if I had infrared camera data and visual data, I wouldn't need a human to do any labeling. I could just train the visual camera, the regular camera data, up by using the infrared to mark what are the areas. Of course, now I need to have an infrared camera and a regular camera when there's going to be a fire. Okay, that's hard. And we were very fortunate because there was a prescribed burn in Kansas at a tallgrass prairie. So we worked with NEON to get a tower ready, which would have both an infrared camera and a visual camera, and instrument so that the burn would happen actually immediately around the tower. In fact, from this picture, you can see that they burned actually around the tower, right? Everything up to the tower. So here is an example of that AI training happening, where we're able to take the real hot data, which tells us exactly what's the temperature is, and map it back here so we can build an AI model automatically. So this is a short video of that burn. So here, Rajesh Sankaran, who's the chief architect for the node, is flying a drone around. And this is the tower that belongs to NEON. We've augmented that tower by adding a particle sensor because we want to understand smoke in the air as well. And then here are our 3 SAGE nodes. And then we also have the infrared camera. And so we have 3 optical regular RGB cameras. We have an infrared camera that has a very large field of view. So now there are several test plots that are run by the university there at Kansas. And so they've burned the square test plots first, and then they're coming back, and here's the instrument truck. And now they've started, and you can see they've burned all the way up to the tower. In fact, they have to move the cables, as the fire comes. And now here is, this is just fantastic, showing how we can get data from the infrared camera and then map it directly back over here. And so this is an example where we do that initial data collection and then have to bring, in this case, we have to bring that data back because it's all that training data. So in this particular case, we had a cell phone modem in that tower, and we wrote all the data. Normally you do edge processing, right? You process it, you don't have to save it all, right? But we wanted to get the training data, so we had to save it all. And we were nervous that something would happen because it's all on an SSD card. So we decided to at the same time it's writing it all to the SSD card, just keep streaming it over with rsync back to the lab, even though it's going to take days and days and days to stream. So we had that, the burn took, all of, 45 minutes, and then we kept streaming the data for days, and we burned up $20,000 worth of AT&T data, right? So, there's a certain data plan where you get to the point where they just keep charging you per gigabyte. So we were in that, no matter how hard we tried. We have, since that time, purchased a Starlink, and we're now, I have it in my backyard, and I've been tinkering with that, which of course will bring the price down to, it's about like $135 a month, so it's a pretty good deal for the RV version. So if you want to be able to move your Starlink around, you need the RV version. So that data, which was that, gigabytes of burn data, we collected and made available through the Wildfire Commons so that people could get that data and begin to do their own AI training against that data. We have a collaboration that's happening with Australia. We just sent 10 nodes to Australia, again, to do this kind of AI at the edge where their scientists will develop their own applications for what's going to run at the edge. Specifically, they're also interested in wildfire, but they're also interested in urban dynamics. We recently started a project with the Ojibwe tribe, which is spread out through the Midwest, but the one we're working with is in Wisconsin. And they're very interested in wild rice, and as climate change continues, what will happen to wild rice, and can we monitor both the environment, but also what's happening in the waterway. And we also recently started a collaboration with the folks with a group in Hawaii, and they're doing it as well to understand what's happening outside in a natural environment area where the ocean and the tides come in. So wrapping up here, so we have time for questions. So the key point here, one is the cyber infrastructure point. We have to build the software systems to do this kind of linkage. And it's very, very similar, the same sorts of things and software infrastructure you have for a supercomputer, we have for the edge. So we have Kubernetes, which, you know, not all supercomputers use, but Linux clusters are very common. It's to use this. We have PyTorch and all the standard tools that come with the AI packages. We have messaging layers, right? And we have a job scheduler, and we'll talk for a minute about multi-tenancy if we have time. We've built this portal that allows you to take a look at the data in real time, and of course, as I said, if folks here wanted to do that, you can go to the admin portal. Here are a bunch of links that show the different portal places, and let me just see here. Okay, yeah, so this is just a couple extra shots that show how these things are built for the ones that are not a software only. So again, if there's a instrument closet, you just have to move in and put a server in there. But if it's outdoors, that wild sage node that I mentioned, then there's a local electronics company that's here in the suburbs. And these two guys here build the nodes from a layout and a kit, essentially, that we've constructed. And then they get put in special boxes here and shipped to Australia or other places. So with that, I'll pause here and I'll mention some of the computer science problems that I think are open questions for us as a community. So one of those is, I mentioned the multi-tenancy problem. So right now, if you run a job on a supercomputer, you get the entire node, right? So the way the job scheduler works, you've probably heard of either space sharing, right, or time sharing. So if you're in a classic time sharing situation, right, the CPU is sliced thinly, you're getting little time slices, right, so you can all share a node. If you're space sharing, which is the way almost all supercomputers run, then you get a set of nodes, that's space, you've gotten a certain space out of all the nodes possible, and you get them 100%. So that means you don't have to worry about someone else using your network, your bandwidth, your memory. You know it's predictable. The problem with that is we can't do space sharing at the edge. And it's because we have many objective functions. We have many things we want to run at the edge. So you saw all the kinds of things people want to run. If you want to do wildfire, if you want to understand cloud dynamics, if you want to see what the water level is, if you're doing hyperspectral or infrared, or maybe you're looking for bats, so all of those things have to share the edge, and that's called multi-tenancy when things share. And so the scheduler that we would want to use can't be a scheduler that says, oh, you get 10 minutes and then you get 10 minutes, because those 10 minutes might be when that interesting bird species arrives, right? So finding out and working out how to share the GPU and how many things you can share before you sort of fall over and need to swap something if you had to, and what the priority of that is, that's a hard problem, and it's still an open problem for those who are in the computer science area. It's a hard and interesting problem we'd love help with. Another one is learning at the edge. So most of the things that I've described are shipping training data to the supercomputer and then processing it and getting a model that you ship back. I'll say that's the easy way, right? But imagine for a minute that how do AI models work? It's a statistical distribution that you've trained on. No matter where you put that model, it's not in the same statistical distribution that all the data was trained on, right? So if you think about, as an example, let's just think about your self-driving car, right, if you had one. All the camera data is taken from this angle, facing either forward, backward, left, or right. You're not taking camera data with your car from 20 feet up, looking down on traffic. So if you take the model that you've built here and move it to a gigantic pickup truck or something else, a semi-truck, repositioning those cameras would change everything. So the question that's an interesting AI learning question is, can we take models, move them out to the edge where they're in a different statistical distribution, and then improve the model slowly over time by learning at the edge? And what does that kind of slow incremental adjustments, and can you do federated learning where you might do that over all the nodes in the network? So these are, again, great AI computer science problems that match the kinds of research that you want to do on the supercomputer with distributed and federated learning with what you might do in the real life with nodes that are deployed and out there. Yeah. Yeah. So we're at the end, and I'd love to hear some questions.
So multi-tenancy and the other problem that you mentioned. So federated learning is really like that's the end goal. But in the meantime, what about like fog computing? So you have a bunch of these sensors placed all around within a LAN, and therefore you can try to figure out something with multi-tenancy using that approach. I don't know if you guys are looking into that. That's my first question. The second question I have, you've addressed the cool projects. What about the actual cyber aspect of it? I mean, these are links, so side channel analysis, they're basically sitting open ducts that can be jammed. Have you guys thought about looking at, from a software-defined radio perspective, turning down the sensor when, that's when something interesting is happening? And so, like, that's what I'm interested in as well. So
Great. So I'll answer the last question first, because and I'll repeat it. There are a number of cybersecurity questions I didn't talk about at all. And so I'll mention briefly a couple of them because it's a very good research area. So the first thing I'll mention is when designing this configuration, we took a very hard and aggressive stance that the nodes themselves have no open ports. So now, it's always a little bit overconfident to say, gee, that makes it secure. We know that's not the case, right? But there are no open ports. So we say, okay, well, how does it work, right? So they only phone home. So because they only phone home, there's no phishing attack here, right? So there's no attack where you're able to talk to it and fool it because it's not listening. It only phones home. Now, how do we then operate it? Well, after it's phoned home, it makes a secure connection that we can then connect back through to make configuration changes. So you can actually SSH back in once it's phoned home. So that gives us, from a security posture, a really pretty sound place where I can put one on a city pole in Chicago and be pretty confident it's not just a simple wireless hack, because there is no wireless, right? It's talking to the AT&T network. If I hack the AT&T network, I've got bigger problems, right? Then I can tell AT&T that, gee, their network shouldn't have been hacked, right? But from a cybersecurity perspective, that's one problem. Now, however, there's an other problem with the cybersecurity. For most of the supercomputers that you guys log into, there's a locked door. No one's going to go in and pull out a hard drive. On this, right, it's on a pole in Chicago as an example. The city told us, well, we ask how high should it be. They say, well, it's got to be at least one hockey stick high. It's in Chicago. But it could be that a node could be stolen, opened up. Okay, what kind of secrets are available? What kinds of things might you be able to do if you have the keys to a node? Another problem, if you're looking for hard problems with respect to that, is if you spend a lot of money training and building a deep learning model, building a model that you ship out to the edge, it might have a lot of worth. That model might represent hundreds of thousands of dollars of work that someone has done in training and building that model, and now it's sitting on the disk, in a node that's out somewhere. So there are good hard cyber infrastructure problems that deserve good computer science research. The one of breaking into, we feel a little bit more confident about because we've taken this very hard stance. The other question you asked was about sort of the fog, or where else can we, how do we solve this multi-tenancy problem? And I would say that no matter how we try very hard, but no matter how we try, we always have more computation than we have resources. So I think of it this way. Someone says, you know, you have a bandwidth problem. And they say, OK, I'll fix your network. And they fix the network. OK, great. And a little bit later, I have another bandwidth problem, right? Because I'm using your network some more, right? I've added some more computers. So we're always short on computation at the edge. There are always more algorithms that people want to run. So even if we link them together with other nodes or provide other resources, we still end up short having to solve the multi-tenancy problem. An example of that, very briefly, is that one of the calculations we want to do for traffic is flow analysis. Flow analysis looks at essentially a movie. It's not looking at a single image. It's looking at several seconds of video and measuring how many cars are occupying the lane, how fast are they moving, are they Amazon Prime trucks, are they taxis, or are they regular pedestrian, drivers, you know, regular driver trucks, right? That computation is actually very hard, and it's non-real time. In other words, 10 seconds of video translates into, you know, 30 or 60 seconds of analyzing. So we really can't share the node with anybody if we want to run that computation. So that multi-tenancy piece remains very difficult for us because we always have more to do than we possibly have at the edge. Other questions? Yeah.
Any examples for healthcare?
Yeah, so the question's about healthcare. So one of our partners in this, it was shown in the video, is the ARM semiconductor, computer design company, architecture company. They don't make chips, they make designs, right, that are then built by others. And their interest initially and very directly was what could be done in a medical setting, right, where you want to process data in real time at the edge, whether it's an MRI or, and there are companies now delivering, racks of GPUs, right, to imaging devices. But what other kinds of imaging devices and other kinds of edge processing are available? So we're not doing that, but it is definitely a motivator in the semiconductor industry because there is a real privacy issue, right? And there's a real data integrity issue, and also the ability to rapidly make decisions, right? Whether someone has, it's as simple as in your home, someone falls and they don't get up. That's the kind of sensor that, again, you don't want a camera watching in your house all the time, but you would like an AI to be able to understand, oh, there's a healthcare problem that needs to be addressed, right? So there's a lot of interest there, but that's not work we're doing right now. ARM is very interested. All the semiconductor companies are, actually. Yeah, yeah.
Right? Are you right now bringing back data through like LTE to the supercomputers?
So each of those nodes is a different mechanism. So in some cases, we're paying for LTE. That's why we had the 20K charge with AT&T. Other places have regular wired Ethernet or Wi-Fi. So on that picture of NIU campus, where it did all those pedestrians, that was using their Wi-Fi network. So, oh, sorry, up there, yeah.
I have one question. For the smoke problem, have you tried to use constructive language model like CLIP?
Use which model?
CLIP or constructive language model because you want to check the smoke. And also, I'm curious about the app IBM. I always thought that they didn't use machine learning, but it was local and you needed to download.
Which didn't use machine?
The app for the bird.
Oh, right.
Yeah, so, because you need to download according to each region, and which it's amazing because I thought, wow, it's not using machine learning and these things.
So you only need to download the model, but then it's local. And so we're talking about the app for those of you who are talking about the bird app. But the number of things, I'll just talk about this for a minute. The number of things that are now that Apple and Android, Google are building into local models that preserve your privacy at the edge on your phone is spectacular. It is just amazing. So as an example, those of you who have iPhones, if you wanted to try this at home or later tonight, you could. Take your iPhone, turn off and put it into, take it off the net, put it into airplane mode. Go to a piece of paper with words on it, highlight it. It will do the image recognition. It'll find the text, and it'll tell you what the word is, right? Without connecting to the network, right? So that model has already been transferred, which is to find text onto your phone. And as an example of this that just made my head spin, I was looking for a particular person in my contacts. It had a very unique name. I searched for it, and what came up on my phone was a picture I took 2 years ago of someone standing in front of the Vietnam Memorial Monument. They were standing in front of the monument. I took a picture of them. The Vietnam Memorial has all these people's names. And it had figured out and parsed all of those names in the background and then replied, oh, well, you're looking for this particular name. Well, it happens to be in this picture, right? Which is both amazing and maybe slightly, spooky as well. But so the Merlin model is running locally, and you can do that, but you do have to download the model for each region, absolutely.
Yeah, now they can recognize pictures of the bird, which I find amazing. But regarding that, do you think we are approaching to something similar to 1984?
It's a great question about the capabilities that we have for edge computing. And is it preserving privacy or not, right? And I think what would be awesome is if for each app, and Apple has started this, right? But for each app, we knew for certain what was being sent home and what was being local. The fact that we might have to do this experiment by turning our cell phone signal off means that we don't have a lot of confidence about whether or not an app is processing locally or remotely. So it would be nice if we knew that very clearly. But yes, that's of course a concern that we should be worried about, right? That we should take seriously.
Okay, just one last question about the fire. Have you tried something like a clip model?
Because I don't know if they've tried that model. It'd be good to, if you're curious about it, the person to talk to is Scott Collis or Ilke, and Bhupendra was the postdoc at Argonne working on the training pieces. They would love to try new models, right? To try new things.
How expensive was to generate the labeled pictures for the fire?
Oh yeah, so these hand-labeled things, I mean, are so tedious, right? We initially had students, summer students, we'd ask them, could you do like an hour a day of, and that's a hard ask, right? Asking anyone to just sort of go through. There are tools, if you haven't seen them, there are tools on the web where it brings up a piece of data and you can find things and you label it and it goes to the next piece of data. But we need to find more automated ways, of course, right? Other questions? Oh, sorry.
Yeah, I guess I've got the mic now. First, thanks. That's really interesting. I have a question about the camera looking at the clouds and weather prediction. So a lot of data goes into weather prediction, like radar sweeps and satellite imagery and thermometers on submarines and all kinds of stuff goes into that. Have you spoken to meteorologists or weather centers about putting that into the ingestion pipelines of any models?
Yeah, no, absolutely. In fact, the scientist who leads that is an atmospheric scientist at Argonne who is a radar scientist and handles the Python interface for radar data. It's widely used as an open source package, Scott Collis. One of the projects we have is looking at this kind of up-facing camera data to the clouds as a predictor of nearby photovoltaic output. So, you know, these weather predictors are pretty, I mean, if you've looked at them on your phone, right, you know, they show what's happening with the clouds right now, but, you know, what's going to happen in 20 minutes or 30 minutes, it's not really available, right? How much cloud would be over me in 30 minutes? That's not a prediction you can get. But with these up-facing cameras and the right kind of model, we can do a better job, and some of the students and postdocs have been working on that. And that's actually really important for the power company. So we're working with Exelon. They're the customer for this kind of science, and they want to know, can we predict photovoltaic output with some certainty, you know, 10 minutes, 30 minutes, 2 hours into the future? And that would help us with grid issues, especially in microgrids. Well,
Thanks.
yeah. Oh, so I guess we have to, we have to follow the mic. Go ahead.
So I was at a conference last week that was a atmospheric science conference, and some people there were saying it would be really cool if they could like get data from commercial flights, like astrophysics data, not astrophysics, sorry, cloud data and stuff. Do you think that would ever be possible? Like to convince them to put it on like an actual plane and take pictures of all the clouds and stuff?
Yeah, so it's a very good question. The NSF, so you know that project I mentioned, NEON, where they have all the towers, that project also has something they call assignable assets. And an assignable asset is essentially a rentable instrument. And one of those, a couple of those rentable instruments, by renting I mean from a science project, are planes. And so they routinely will allow a scientist to instrument the plane and then, you know, request that the plane, you know, charging their grant, fly in under these circumstances to gather data. And so we have been talking to the NEON folks and others about, okay, how might we get other kinds of data that's more relevant, you know, to this? And certainly the folks who do wildfire that feed that data into Ilke Altintas project at San Diego, they try to create a live fire perimeter and then use that for the supercomputing computation of where the fire will go next based on weather. And so that's another example of this kind of quick fly. Can you get something up and take images and then process it in near real time? Oh, she's up.
Hi, I just wanted to know about the Tesla car example that you gave for having different distribution for training and testing. Did you think about trying transfer learning or domain adaptation?
Yes, that's exactly what we're doing. Yeah. So, and in fact, some of the discussion. So you saw that example where we have an infrared camera and a regular RGB camera, and you can do this kind of training right from one to the other. The same is happening for the cloud data. So there's a type of instrument which is a sort of laser-based instrument that can look up, a LiDAR, that can look up and tell us about what's happening with actual altitudes. And you can then use that to train in a camera, which then is much cheaper to deploy. And one idea that's come up is to do the same thing for camera data that is taken from different perspectives. In other words, build the model, put it where it has been trained, then put another node somewhere else that can see the same scene and have it build, again, with transfer learning, be able to modify what's happening on the other node so it learns what it's seeing from this node, right? So this kind of pairing and learning is, I think, is going to be important. But the computational problem is that if you thought inference was hard at the edge, training is really hard at the edge, right? So it turns out that it's been challenging for us to get enough cycles at the edge to do real training. I think we can change weights, in some layers, but to sort of retrain is not going to happen, right? But so we might be able to modify things.
But transfer learning can help you just train the last layer or maybe
right,
the deeper
or inject
layers.
new layers. Yeah, absolutely.
Yeah.
Yeah, very, very good point.
I have a very small question. From computer vision perspective, has there been work in modeling whether you can predict if somebody's becoming hostile or picking out their gun and going to be a danger to society, and can there be models to
so
predict that?
it's a very good question. No, it's an excellent question, and I do know of one project, and it's not anywhere that it's not related to what I'm doing. I've talked to the investigator, and I won't say what city it's in, but they were interested in, would it be possible to predict when people are contemplating jumping in front of a train at a train crossing, right? And so they've had a number of tragic examples where people stand near the tracks, and there might be signals in how they move and with their posture. Maybe there's a way to have sort of an intervention that says, wait, what's happening? Why are they behaving that way near the train tracks? And so I think there are probably other projects that are working on similar things. Again, without a human, without streaming data, you can't do this by streaming all the data to a cloud and having someone look at it. That's not going to work, right? It has to be AI that's happening at the edge, and it has to be maintain privacy. It's got to be able to signal somebody nearby that says, wait, there might be a problem happening on track 5, right? Please go, see what's happening. So I think there are a variety of situations where those kinds of things. Another example that you've probably already seen on your iPhone or another's is they're analyzing your gait, your walking, right? And people who have balance diseases, diseases that impact your balance, it can be detected, right? And that's, again, could be done semi-anonymously, right? It's running it on the edge. It's computing on data that was collected and possibly even simulated, and then run at the edge and can do some improvements, right?
Thank you.
Thank you for the talk. I had a question about your clouds project. Is it really necessary to train machine learning projects, or do you see an improvement over classical computer vision algorithms to calculate, for example, the velocity of the clouds?
Yeah, no, it's a good question. So the standard, I'll say, sort of computer vision algorithms, Kalman filters and other things that can be applied can give you some dynamics, right? And dynamics is the key here that people are very interested in. But our experience so far, and I think this is an open question, is that the real behaviors that you want to see with especially with multiple layers of clouds and what happens in the middle of the morning versus at night and the lighting changes, the standard computer vision algorithms have, as you know, tremendous problems with lighting changes, and deep learning tends to do better with that. And so I think there is a place where these will be combined, right, where there are filters that happen with, well, I say, classic computer vision. And if you're interested in that problem, Nicola Ferrier leads the AI team for this project, and you could send her an email, and that's actually her area of expertise, so she would love to answer.
Of course, yeah, I'd love to ask her. Thank you.
Some of the data you're collecting is very financially valuable. For example, it's known that a lot of hedge funds study satellite images to measure car movement between businesses. Have you considered selling any of this?
No, no. So, so all the data is public. The exception is that images that are from down-facing cameras in Chicago are not made public, but they can be used for research. But they're infrequently collected. They're only training images, right? So of course we couldn't possibly afford the 20K for a couple hours of data, right? So we don't collect streaming data from any place in Chicago. We collect a few training images to make sure that the models that we're using are correct. For imagery that comes out in the wilds of Colorado or other places, deer and raccoon have no privacy. So, all of that data you could get, and clouds as well. Okay, thank you very much.